Now, a second way of selecting ROIs is to use some kind of functional definition, meaning to use your functional data and some kind of contrast between condition A and condition B to then select what part of the brain is relevant for the ROI analysis. Now, see, the problem when you do this is now known as double dipping. And the idea is the possibility that the way in which you selected this ROI, the contrast that you used to select this ROI, might not be independent of the ROI analysis you're planning to do later. And if they are dependent, you actually risk that your result is fully circular, meaning you select an ROI because it responds to a certain task, it responds to task A versus task B, and then inside that ROI, you say, oh, look, inside this ROI, I get a crazy result when I compare task A to task B. Of course, that's how you picked it. Okay, I'll give you an actual brain example in just a second. But very important, we really do not want any double dipping. Okay, this is really key. So it's important, it's crucial that the way in which you select the ROI must be completely orthogonal, completely unrelated to the comparison that you're planning to do with the ROI analysis. If that's not the case, if the way in which you're selecting the ROI is not entirely orthogonal and completely independent of the analysis you're planning to do, then you're double dipping. Here's a couple examples of how all of this came to pass. Now, these are a couple of experiments that I want to show that actually ended up unknowingly doing some circular inferences. Here's this particular example. So in this study, what they did, and they're showing it right here, they're showing the results for the whole brain results for looking at faces versus looking at houses. And then see, this piece of the brain right here turns out to be very active. And so what they then do is they say, okay, so let's take this piece of the brain right here, and now let's do an ROI analysis in it. And what's the ROI analysis that they do in here? Faces versus houses. And they say, oh, look, crazy effect. Wow, inside here we discover that there's a significant main effect of stimuli if it's faces or houses. As they say, that the post-hoc analysis in the peak voxel revealed a significant main effect. But if you think of it, that's exactly why we chose that voxel. We specifically chose this voxel right here where the cross is, because that voxel was the voxel most active in the comparisons of faces greater than houses. So is it surprising that when we look at the voxel that is specifically picked because it is significantly more active during faces than houses, we then look inside that voxel and we find that it responds more to faces than houses? It's not an independent analysis. It's exactly the same analysis, just done on the ROI, right? The way in which we selected the ROI leads to a completely circular chain, to a completely circular inference in the ROI analysis. Of course, we get a main effect of faces versus houses in that voxel. That's why we picked that voxel, because it's the voxel that responds the more at the full brain level in faces versus houses. See, and this looks almost fun and quaint at this point, but people used to do this all the time. So it was not as obvious until somebody pointed this out. And here's another example. And this was one of the many so-called papers that sort of led to the idea of voodoo correlations. And the idea of voodoo correlations came out of the fact that somebody noticed, Ed Vull noticed, that there were a remarkable number of fMRI experiments that ended up showing correlations that were extremely high. It's correlations in the range of 0.9, which it's an extremely high correlation. It doesn't happen often to get correlations that strong. And so it turns out in a large subset of those studies, the correlations were that high because they were circular, because the voxels within which those correlations were looked at had been selected because they had that property. See, for example, in this experiment, and we can only look at sort of the central result and the one on the right. The panel at the bottom in the middle is showing which voxels correlate at a full brain analysis with extraversion. And then if you take these voxels and you turn them into an ROI and you put them here, you notice that they correlate a lot with extraversion. Now, how surprised are you? And see, there's a really high, the correlation is 0.71. It's entirely circular. We specifically picked this ROI because it correlates with extraversion. It's not very surprising that if you then take this ROI and do an ROI analysis, you find out that on average, the t-score in here correlates a lot with extraversion. Of course, that's why we picked that ROI. Completely circular. Okay? So again, it sounds almost funny now, and you'd think, oh, I would never do that mistake. But we've been making this mistake for a long time until somebody pointed it out. And this paper and the previous one were both published in Science. So how do we avoid double dipping and getting into voodoo correlations? Well, the simplest way is to just not do an ROI analysis and only do a whole brain mapping, what sometimes people refer to as a non-selective whole brain mapping. But I do think there's a lot of value to ROI analysis. So I'd rather be able to do an ROI analysis and just find out good ways not to fall into the trap of double dipping. And the key aspect is make sure that the way in which you select your ROI is independent of whatever you want to test with the ROI analysis. For example, use an anatomical mask. That probably is one of the simplest. If you want to use a functional mask, a functionally defined ROI, make sure that you use different functional data to select the ROI compared to the functional data you want to use to assess that ROI. For example, use data from a prior experiment. Use data from somebody else's experiment as a localizer. Or maybe use data from a different run in your experiment. So people often do what are known as functional localizer tasks. Let's say that I care to, let's say that my experiment were about something on how the part of the brain that responds to faces is engaged into, I don't know, some other aspect of cognition, expertise. What I could do is the first run of my experiment could be a functional localizer run. All I do in that run is I show faces and then nothing, faces, nothing, faces, nothing. And then I use that contrast to isolate what is the part of the brain in each participant that responds to faces. This way, I select my ROI, and then I will apply my ROI to different runs when I'll be doing some other task of interest. And I will want to assess that, whatever is the contrast of interest in the ROI that I defined on a different run, on my functional localizer. Alternatively, you might be able, if you really can't do any of that, you maybe could be able to do something like use even trials to select the ROI and odd trials to assess your hypothesis, and then maybe do it both ways. However, I should warn you, and that's why there's an asterisk, you might want to be careful if that's what you're planning to do, just because who knows that there might be ways in which nearby trials could still contaminate each other. And so leak information into the selection process. But again, the key message being, you have to ensure that you can make a rational case when you write the paper that the way in which you selected the ROI is independent of the ROI analysis. And finally, I won't go over this, but I'll leave you with this. This is a wonderful chart by Nico Kriegescourt with suggestions of things that you can do in order to avoid voodoo correlations or circular inferences, really. And many of these are the points that I just covered, but he goes into a little more detail. And in fact, in the next slide, I link the paper where he discusses this, which is a wonderful